Hello, I am Zibo Zhang. I'm glad to present our work called Vectorizing line drawings of arbitrary width via contour-based topology reconstruction. Vectorization is a commonly used technique for converting raster images to a vector format so that the image can be rescaled without any quality loss. Compared to raster images, vector graphics are of relatively small file size, which is suitable to be used in various applications, such as web-compatible images and illustrations. Besides, with the vector representation, one can easily edit the line drawing, such as changing the color and the thickness of each individual line. In this work, our goal is to take a raster line drawing as input and output a vector line drawing. A simple but commonly adopted method to get the center line is using the thinning algorithm. However, the output of thinning algorithm usually can't express the actual geometry of the raster line inputs, as shown in the red box. The root cause of the problem is the design flaws in the original thinning algorithm. The algorithm may squeeze the skeleton estimation at the locations of junctions or endpoints. Consequently, the estimation skeleton is not correct at these locations when the line is thick. So we want to propose a new method to achieve the goal of extracting the center line accurately. Including thinning method, there are some related works that need to be mentioned. As stated before, the thinning algorithm is a morphological method which will have some errors at the junctions. Favreau and others use global information to resolve ambiguities at junctions. This method tends to output over-segmented and oversimplified results. Moreover, it cannot handle complex junctions and non-closed strokes without user interaction. Best-Meltzer and others reconstruct the topology and vectorize line drawings based on frame fields. But the method cannot handle thick line strokes properly, sometimes causing double estimation of skeletons. Gore and others proposed to reconstruct the topology of line drawings in a junction-tailored two-step approach. Their model architecture is unable to handle very thick strokes. The first reason is that the skeleton extraction model has a limited receptive field and cannot handle thick strokes well. The second reason is that the junction of thick strokes will confuse their line ordering model, so the topology reconstruction will also fail. To analyze the topology of junctions composed of thick lines, we observe that the boundaries of the lines can usually provide useful hints in making the decisions. These are two similar line drawings where the left one is composed of two curves and the right one is composed of three curves. While it is not easy to differentiate the two cases using the thinning algorithm, the top boundary curve actually shows clear hints of the topology of this junction. In the left one, the top boundary curve is a smooth curve, which indicates that the horizontal curve should also be composed of only one curve. In the right one, the top boundary curve has a sharp turn, which indicates that the horizontal curve should be composed of more than one curve. So the correct output can be obtained by using the boundary information. Given a raster input line drawing, we first binarize it into a black and white image to map each pixel into either a line pixel or a background pixel. Then we extract the skeleton of the line pixels via the traditional thinning algorithm. Despite the imprecision of the extracted skeleton, The boundaries of the input line joins can be precisely extracted and provide significantly valuable hints to obtaining the precise skeleton location and topology. We constructed segments from pixels for both the skeleton and the boundary. These constructed segments and their mutual connectivity actually shows an initial guess of the topology of the line drawing. However, this initial topology is usually incorrect at some locations. We further refine the topology of the center line by removing redundant skeleton segments. And finally, we reconstruct the wrong part of the remaining skeleton segments. After this series of steps, the output can well conform to the human's perception. Now we elaborate on the details of each step. Due to the discrete nature of raster pixels, the identified skeleton segments are not smooth. They may provide incorrect information of local properties, such as tangent and curvature. Therefore, we fit each raster skeleton segment with an optimization-based smooth spline. Similar to the skeleton, we also implement such operation for the boundary. With the constructed skeleton topology, we can observe that some skeleton segments are not expressing the actual geometry of the raster line inputs. These unreliable line segments can be categorized as spurious spikes and spurious connectors. We need to remove these redundant segments caused by the thinning algorithm and reconstruct the remaining segments. We proposed to eliminate these unreliable line segments based on geometry constraint assumptions and elaborate the following procedures. To detect spurious spikes, we formulate two criteria: skeleton-initiated tangent consistency and boundary-guided skeleton completeness. We first introduce the tangent consistency criteria. This is two cases. The thinning algorithm outputs a real spike and a spurious spike. To distinguish these two situations, one critical observation of the spurious spike locations is that the tangent direction between the boundaries and the skeleton is usually inconsistent. Let's first take the lower left figure as an example. For each point on the spike, we first find its corresponding boundary points, and then compute its tangent consistency scores. As shown in the lower right figure, spurious spikes and their corresponding boundaries tend to have low skeleton tangent consistency scores. If the scores of all points are less than a certain threshold, we will mark the segment as a spurious spike. However, tangent consistency is not sufficient to cover all cases. The second criterion is boundary-guided skeleton completeness. Let's observe a new case. This case cannot be detected with tangent consistency, so we need another criterion. As shown in the bottom left figure, the purple and brown boundary of the real spike segments correspond to only one skeleton segment, while in the bottom right figure, the purple and brown boundary segments correspond to more than one skeleton segment. So when such boundaries correspond to more than one skeleton segment, we mark it as a spurious spike. With two criteria, skeleton-initiated tangent consistency and boundary-guided skeleton completeness, we can complete the detection of the spurious spikes, and then we need to detect the spurious connectors. We still use tangent consistency to detect spurious connections. As shown in the figure, We mark the pixels with consistent tangents as green and those with inconsistent tangents as red. The animation shows the labeling process. In addition, boundary-initiated tangent consistency is also used to detect spurious connector. As shown in the animation, boundary-initiated tangent consistency is similar to the previous tangent consistency, with the only difference being that the starting point becomes the boundary point. If both the tangent consistency scores are less than a certain threshold, we mark the segment as a spurious connection and remove it. After removing the spurious spikes and the spurious connectors, we expect the topology of the lines to be correct. However, the thinning algorithm may create fluctuated curves near the junction, which is a false estimation. Fortunately, we can still recover almost accurate junction locations and tangent values with the aid of boundaries. Correctly speaking, for each junction, we find all skeleton segments connected to this junction. Then, for each of these skeleton segments, we find the closest tangent consistency point to the junction as the cutoff point. As shown in the animation, we intercept part of the boundary segment corresponding to the cutoff point, translate and rescaled it as a new segment, and paste it back to the missing location to finish the patching. The two skeleton segments will be merged into one skeleton segment in the topology after the connection. Similar operations are performed at the unreliable part near the line endpoints. But there are still some skeleton estimation mistakes that cannot be recovered due to the absence of boundary correspondence. In this case, we can only use the aid of the topology for construction. Also, we find the closest tangent consistency point to the junction as the cutoff point. If the tangent directions of two cutoff points are collinear, we instantly connect the cutoff points with a straight line to recover the topology and merge the corresponding skeleton segments into one segment. For those non-matched skeleton segments near the junction, we proposed to enforce the topology reconstruction with a skeleton extrapolation strategy. To do so, we first remove the tangent inconsistency point near the junction. Then we apply a polynomial curve fitting to the skeleton segments to approximate the analytical representation of the skeleton segment. After the curve fitting, we extend all broken skeletons from the cutoff point until they reach the boundaries. During the extension, the boundary topology is automatically restored with the skeleton extension reconstructing the junctions. Finally, we clean up all overextended skeletons from the farthest extended junction point to the boundary to conclude the topology reconstruction. This is a visual comparison of our method with existing methods, and we can see that our method has significant advantages. Our method also works for more complex cases. We compared with the existing methods on line drawings of different line widths. When the line width is small, the effect of each method is relatively similar, but with the increase in line width, our method has obvious advantages. Our method achieves the best results in the average scores of all the line widths. There are three limitations to our method. While the boundaries of the line drawings are usually smooth and give clear hints about the topology of the lines, it happens that the boundaries of the lines are not smooth because of artistic styles or low-quality images. Since our method is highly dependent on boundaries to obtain the correct topology with precise skeleton locations, it will fail when the boundaries are not smooth and unable to give correct hints. Moreover, some very short and tangent inconsistency skeleton segments might be mistakenly classified as spurious spikes and removed, as shown in the nose of the bear. Our method is not designed for sketch images. Sketches require semantically simplified lines, and our method preserves each curve faithfully. In this work, we proposed a boundary-based topological reconstruction and vectorization method to convert a line drawing of arbitrary thickness into a vector representation. We propose to first identify whether the initial skeleton pixels are accurate by analyzing the tangent consistency of the skeleton pixels. Then the topology of reliable skeleton points is retained, and the topology of unreliable skeleton points is reconstructed using the boundary and the topology. Our method can be applied to more cases if line drawings of specific art styles are pre-processed using a smoothing algorithm. Thank you for listening.